Hi everyone, we are Group 129. Our project is a transformer based medical diagnosis assistant using BioBot to predict diseases from natural language symptom descriptions. Accurate diagnosis is essential in healthcare, but the complexity and overlap of symptoms often lead to misdiagnosis. On top of that, medical data is typically unstructured, like physician notes or EHRs, which are hard to interpret and prone to error. To address these issues, we propose a transformer based assistant that analyzes symptom text and predicts possible diseases. Our system aims to help healthcare professionals with quick, interpretable, and reliable AI support. We used a Kaggle dataset with diseases and symptoms in separate columns. Each row lists a disease and up to 17 related symptoms. We later converted this into natural language input. Inputs are full symptom sentences. We pre-process, tokenize, and feed them into BioBud. The model predicts possible diseases with confidence scores as output. We then explored the data and found the most frequent diseases and symptoms. This helped us to understand the class imbalance and data structure early on. Here we have plotted the top 10 most common diseases and the top 10 common symptoms. We then visualize symptom pairs that often appear together in a heat map. This helped us to design better inputs by considering natural symptom groupings. In the previous phase, we trained a logistic regression model and the TF-IDF method as our baseline model using the structured data. It achieved nearly perfect accuracy on the training set. However, it struggled with unstructured real-world inputs where symptoms are phrased in free text. This limitation highlighted the need for a language model like BioBot, which we introduced in phase 3 for better generalization and understanding of the natural symptom language.
Our original dataset was structured in a wide format with one column for the disease and up to 17 columns for individual symptoms. This format isn't suitable for language models like BioBot that expect natural text as input. So we converted each row into a sentence, such as, for example, a sentence input could have been, I've been experiencing itching, skin rash, and nodal skin eruptions. This type of transformation simulates how users would describe symptoms in real life. We then used label encoder to convert diseases into numeric classes and applied the BioBot tokenizer to process the sentences. Finally, we injected some noise by paraphrasing. For example, we changed terms like vomiting to throwing up or like fatigue to tiredness to simulate varied use of phrasing. This would make a model robust to real world natural language variations. To model our task, we fine tuned the BioBot based cased V1 model, which is pre trained on biomedical data. We chose this BioBot model because it's commonly used for tasks like disease classification, clinical NER, and medical QA. It understands symptom expressions effectively. So our pipeline starts with natural symptom sentences. The tokenizer converts these to token IDs and masks. BioBot then encodes the input and the classification head maps this to one of the 41 disease classes. For training, we used Hugging Faces Trainer API and configured it with the batch size, 3 epochs, and logging. The model was trained on clean natural sentences and tested on paraphrased and partially dropped symptoms. Coming to the final results, here you can see our classification report. Despite the added noise, the model performs very well, achieving 94% accuracy, with most diseases having very high precision and recall value. This shows this model can generalize well even under realistic noisy conditions. This confusion matrix shows the actual versus predicted disease labels. Most predictions fall on the diagonal, indicating correct classification. On the left here, we have the precision recall curve for the top 3 classes. The curves remain high, suggesting strong performance even across different thresholds. And on the right is the ROC curve. The AUC is 0.99, which means even with noisy and paraphrased inputs, the model maintains high discrimination ability. This confirms that our strategy of testing with noise helped prove the model's robustness and real-world readiness. Our model achieved a top 3 accuracy of 96.3%, a log loss of 0.12, and a Cohen's kappa score of 0.94, indicating a strong prediction confidence.
Yeah, so I'll be giving the demo. So we get an option to enter the symptoms in the terminal. So let's say I use this one, that I'm experiencing body aches, nausea, and yellowing of skin and eyes. Once I enter it, the model predicts the disease as chronic cholestasis. I'll show another one. So here the disease is predicted as arthritis. So as you can see, we can enter the sentences, different sentence structure. Uh, Moving on to the prior work, two of us have a previous prior work experience from our undergrad projects. These are the references that we used for our project. Thank you.